Okay, we're going to be working on a problem that's similar to what you're going to see on the homework. So we're given this sequence, a to the n is equal to n over n plus 1. So we could rewrite this as n equals 1 to infinity for a sub n. So we want to prove that the limit as n approaches infinity for our a to the n, which is n over n plus 1, approaches a limit of 1. All right, so we start off with stating if and only if, or if for if and only if, for all epsilon greater than 0, there exists an n greater than 0 such that if our sequence n has to be greater than where our boundary n is, uppercase n is, and that instead of f of x minus L, our sequence is a to the n minus L is less than epsilon. Then we can say that our limit, then we can say our limit as n approaches infinity for n over n plus 1 reaches a limit of 1. And so we can say that it converges to 1, to our limit. So we have to ask ourselves, what has to happen for this statement to be true? So to start with, we begin with scratch work. We have to find what this n is. Once we find what that n is, then we can go back and state our proof. So for our first step, we write this as a to the n minus L is less than epsilon. So again, instead of f of x minus L, we use our sequence a to the n. So now we're going to replace our a to the n and our limit. So that'll be a to the n is n, right? A to the n is n over n plus 1. So we put in here n over n plus 1 minus our limit, which we said is 1. And that's less than epsilon. Okay, so from here, what we want to do is we need to combine these terms. So we need a common denominator, which is n plus 1. So we're going to write n plus 1 over n plus 1. So this would be the absolute value of n over n plus 1 minus n plus 1 over n plus 1. And that's all less than epsilon. So from here, we distribute that negative because the negative has to go into the entire numerator. So that'll be n minus n, and so it distributes to the n and the 1. So this becomes a minus 1. So we're distributing that negative to both terms. And that's all over common denominator n plus 1. And we're still in absolute value here. Well, n minus n is, they cancel, right? I mean, they go to 0. So now that leaves us with just negative 1 over n plus 1. That's less than epsilon. And since we have an absolute value, your result is always going to be positive, so we can drop that negative. So it's just 1 over n plus 1 is less than epsilon. Now let's examine this for a moment. We know that with fractions, 1/2 is larger than 1/3. So if n were 2, then n plus 1 would be 3. So therefore, 1 over n plus 1 is smaller than 1 over n. So going smaller is okay. We can do that because we want it has to be less than epsilon anyways. So we're saying that 1 over n plus 1 is less than 1 over n. So we're replacing 1 over n plus 1 is now, we can just use 1 over n is less than epsilon. Because when we're looking at our limit, right, and here's epsilon, limit, here's our limit, and our limit plus epsilon, and limit minus epsilon, we can go smaller. We can go smaller, we can get closer to that limit. So going smaller here is okay. So we're using 1 over n now. All right, so from here, because it's always positive, we can drop the absolute value, and it's just 1 over n is less than epsilon. And so we're pretty much doing what we did the last problem, where now we just multiply n to both sides. It's hard to see that. There we go. And so the n's cancel here, and we get 1 is less than epsilon times n. And that's kind of hard to see, so use a larger, there we go. So now we divide both sides by epsilon, divide by epsilon, and we get n is larger than 1 over epsilon. So we can flip that, make that n is greater than 1 over epsilon. Okay, so since we know that n, our sequence n, is larger than our boundary n, well then that's going to be larger than 1 over epsilon. Okay, so now we're ready to write our proof. And so with our proof, we're going to be working backwards. We're going to work backwards. And once we get to this point here, then we've proven it. So from here, our proof. So far, this is just a scratch work. We haven't gotten to the proof yet. But the proof is easy because the legwork is all in the scratch work. Proof. For all epsilon greater than 0, we choose a boundary n greater than 1 over epsilon. Then for all sequence n greater than our boundary uppercase n, we have the absolute value of n over n plus 1 minus 1 is less than epsilon is true, excuse me, is true because we have, and then now this is where we work backwards. we have here 1 over n is, so since we have here, since we said that n is greater than 1 over epsilon, since our boundary n is greater than 1 over epsilon, then our sequence n is definitely going to be greater than 1 over epsilon. So if we multiply epsilon to both sides, right, we get epsilon times n is greater than 1, and then from here we can divide n to both sides, and so that's epsilon is greater than 1 over n. So basically we can flip that, right, to where we have here 1 over n is less than epsilon. So all we did was we just switched it. Epsilon is still greater on the greater end of the inequality, and 1 over n is still on the smaller end. So basically we've gotten the same position as where we were here. So we're working backwards now. So we're working backwards in this sequence, and eventually we're working backwards up to here. So, and this is the proof part. So now from here, we can say that, we have our 1 over, from here we can go ahead and put in absolute value 1 over n is less than epsilon. And because it's an absolute value, it's not going to be any different than if we put a negative 1 there over n is less than epsilon. So now if we said, all right, if we have a negative 1 and then we add an n and subtract an n over n, then that's no different than just negative 1. Well, why are we doing that? Because we want to get to here. We want to get to here where we have n minus n, positive n minus n is a minus 1. So all we're doing now is switching the n and the negative 1. So that's n minus 1 minus n over n, and that's all less than epsilon. Well, this would be n, and now we're going to switch the negative n and the negative 1, so that's n minus 1 all over n less than epsilon. Okay, so we have to get to this n plus 1, right, in the denominator. So the n plus 1 is going to be smaller than n, so that's okay. That it's okay to be smaller. So therefore, we added that n plus 1 on the denominator. So now we can split it. And now we have n minus n, and so now we're factoring out the 1, so that becomes n plus 1 over n plus 1 and n plus 1. So is less than epsilon. And so now n plus 1 over n plus 1, that's just 1. So we have here n over n plus 1 minus 1 is less than epsilon. So we've proven that this is true. So therefore we've proven it. We've proven that as long as we can get to this, we can get to the epsilon to get a to the n minus our limit that is less than epsilon, then we've proven it. And that's our video for this proof.